Hello everyone from my side as well. I hope you can hear me all well. Thanks for joining. My name is Victor Hernandez Moreno. I am recently upgraded my position at ACC as a CI now in the program 1 for biomimic cobots. And I'm also a lecturer at the University of Technology. Today, I would like to start the presentation with a quick question, because it happens to me sometimes when I look at a robot just from a mechanical perspective, there's actually nothing very magic. It's only a serial connection of motors, right? So maybe it happens to you as well. So the magic and the fascinating part of robots is actually just coming from the correct programming, which basically results then in the complex and smooth behavior we all love about robots. So today I would like to dive into a promising robot programming technique, which is called learning from demonstration. And this one happens to be one of my core research fields in my recent PhD candidature. So if I jump to the next slide somehow. Yeah. So in today's agenda, I would like to start with recapping a little bit on the traditional robot programming and some technological advancements. Then I will dive into what learning from demonstration actually is, followed by a literature review I've conducted for learning from demonstration, its obstacles and opportunities, specifically in the industrial assembly sector. Finally, I will then go through some recent contributions in this field and wrap up with some future work I'm planning to do, or actually have started to do, and a concluding statement. That's all good. Let's dive into this first part where we talk a little bit about traditional robot programming. So this might be probably all familiar to you all, but I just wanted to recap on it and then extend it on the other ones. So the traditional robot programming approaches, we can find here three main approaches. One of them is the lead-through programming. As you can see here in the picture, it's basically that a human uses the teach pendant, which is connected directly to the robot controller, to move the robot to specific points, store them, and then the robot can afterwards go through these points in order to fulfill the task the human had intended for the robot. This can be quite time-consuming, especially if you want to program very complex motions. And in this scenario, you also need the robot during this programming phase. So the robot can't do any other stuff in the meantime. This last point, or the last 2 points, actually applies as well to this so-called walk-through programming. This is particularly of interest for collaborative robots, which is often used with collaborative robots, but it happens in traditional robot programming as well, where the human operator basically moves the physical robot through the desired motion to fulfill the task. So the robot comes into this passive mode where only gravity is compensated, and the robot can then be moved freely. So in this case, again, it can be quite challenging when you have very complex tasks, or for example, if you have a humanoid to show like multiple arms moving, that can be quite challenging. And you need the robot as well being present during this programming period, and the robot can't do other stuff in the meantime. Separate to these ones is a little bit this offline programming method, which basically looks into an entire simulation of the entire workspace. You need very specific simulation software to do that. The robot is free to do whatever it is intended to do, but it needs a lot of experience as well. So technological advancements, we can mainly see these ones in the interfaces or the input modes in order to communicate with the robot, to program the robot. So we can see here, for example, and you've probably seen several videos about it as well, of like using vocal commands, gestures, facial expressions, or even eye tracking or haptics. The new part as well is the reality enhancements. So using augmented reality or virtual reality in order to extend it to this 3D world. But in general, using also these input features, in most cases, the programming is still very dumb. So it looks into recording and just playback whatever was demonstrated. And it's not acting on some kind of environmental changes or whatever. So in this kind of scenario, I would like to introduce kind of this new, let's call it new for now, method of programming a robot, which is called learning from demonstration, which basically looks into how can the robot be programmed similar to how you would teach another human a new task. So let's dive into learning from demonstration, what it actually is. So as I mentioned before, the idea of learning from demonstration is generally still that the human has some kind of knowledge of the task and wants to transfer this knowledge to the robot such that the robot becomes capable of performing this task. In this sense, the idea of learning from demonstration from the human's perspective is now that the human sees the robot as another human, or like can program the robot as he would teach a new task to another human. So it's basically targeting specifically the non-robot experts and looking into intuitive communication and natural ways of showing the task. Beyond this, we have on the robot's perspective, from the robot's perspective as well, not just mimicking the task, what I mentioned before with the traditional programming methods, but also it extends into the capability of translating the task knowledge into new situations. So this can include, for example, the relocation of objects. So if I show, like, for example, moving an apple from A to B, but when the robot is to be taught to do the task, it can also do it from A to C. It also includes any kind of environmental changes. So if the scenery in which the task was taught has changed to a situation in which the robot should perform the task, the robot should be still capable of doing it. And the last but not least, let's assume like some kind of assembly task. We want to also incorporate the capability of the robot to look into task changes. So doing the same task with slightly different objects. So imagine you have an assembly task, you do it all the time with M4 screws, but then you have a product variation, and it happens to have M6 screws now. So the robot should still be capable of doing it. Similar to an co-worker which can translate this knowledge to another task. So in order to get there, the learning from demonstration research community has established this kind of procedure. So we typically have these three phases of demonstrating, then learning, and then the reproduction. And these two actors, so the human and the robot, are interfering in these phases on a baseline like this. So we have the human obviously performing the demonstration while the robot is observing what the human is performing. Then a learning phase where the robot tries to understand the task itself, and then to translate it and perform it in an autonomous reproduction. We can extend this broad image to also including the human in the learning and the reproduction phase. For example, in the learning, the human could supervise the learning and maybe make it more efficient. So if the robot learns something wrong, the human could intervene and basically guide the learning. And then in the reproduction, we have basically that the human can still monitor and collaborate with the robot. So generally speaking, I've talked about like this new learning from demonstration or like this new programming method, but it's actually quite old. So in this historic line, I've started with the first introduction of a robot in an industrial setting in 1961. And then in the 70s, the teach pen and the computer-aided engineering softwares and lead-through technologies were invented. Learning from demonstration, or the original programming by demonstration, was already established or like invented or desired in the 1980s. And then just with the emerging aspects of machine learning and then the expansion to collaborative robots, it extended into more variety of applications, but the original idea of learning from demonstrations pretty old already. However, even though it's pretty old in research and we have plenty of papers since then, it still hasn't applied much in manufacturing industry. So it has not gained a robust standing in the manufacturing industry. So why? Let's have a look into the outcomes or the findings I had for learning from demonstration in industrial assembly and the related obstacles and opportunities. So in this one, I was basically looking into recent publications about learning from demonstration in industrial assembly or in assembly tasks. And I've looked into some statistics on what methods have been used in these three phases. So looking in the demonstration method, into demonstration phase, we typically see three main aspects to be used. So the first one and the most used is kinesthetic teaching, which is similar to the walkthrough programming, as I mentioned before. Passive observation means that the human is typically equipped with some sensors, so he can move to some extent freely and present a task until operation is remote control of the robot. So interesting here, even though we have this idea of learning from demonstration to be very intuitive, in research we find the majority of demonstration realizations still using kinesthetic teaching. In the learning phase, there are a bunch of different techniques, but we can classify them based on the outcome of the learning. So we can see here, for example, the policy, which is the majority of outcomes that have been used in the context of industrial assembly, which is basically just a trajectory to follow. A plan suggests that the learned task is more high level, so picking up this object and placing it somewhere else without knowing how to do that. And reward is related to reinforcement and machine learning aspects, but it's not as seen as other techniques. Quite interesting when I was looking into the actual sub-skills or skills that were used in the experiments or achieved in the experiments, I've divided it into joining sub-skills and mating sub-skills. And with this, so you see in these two separate graphs, and then the color coding was an analysis of how related these experiments were to industrial practice or practical industrial applications. So for example, these 7 documents looking into stacking, they were obviously pretty unrelated because they were just stacking blocks on top of each other. So in this kind of area, we can see that we have a lot of papers just looking in pack insertion and only a few looking into mating subskills. But in industrial assembly, you basically need a lot of subskills to fulfill one assembly task. So in this study, I was also looking into how well learning from demonstration actually compares to industry proven and used workforce instructions. So with the idea of using learning from demonstration in the manufacturing sector, it is important to see how much does it relate to industrial practice in training a new co-worker in a new assembly task. So we can see here on the left side, we have the learning from demonstration phases, which I mentioned before, the demonstration, learning, and reproduction. And if we compare this to one of the methods that is used since the 50s in Germany or in the German industry, which is called the 4-step method, or the German word below, it is actually quite similar. So in this 4-step method, we have a preparation phase, then a demonstration explanation, an execution and explanation phase, and then finally the practice. So if we compare these ones quickly, we can see basically on the right side, the first step, the preparation phase, when you instruct another human, you are actually looking into defining a suitable learning objective, and the instructor has to really know what the learner's capabilities or existing knowledge is. That's a little bit missing in the learning from demonstration, but other than that, the other 3 aspects are quite similar. One aspect here to see as well, instead of demonstration and execution, on the right side only, we have specifically that it includes the explanation as well. So in the instruction of workforces in industry, you typically have the physical performance, while simultaneously as well a verbal reasoning or justifying what the key aspects are. So this simultaneous communication channels and using multiple ways to communicate is largely missing in learning from demonstration. But overall, it looks quite similar and makes it promising to be integrated into manufacturing practice. So the findings in this little literature review was basically what I mentioned before. Learning from demonstration does align well with workforce training, which promotes a smooth integration into manufacturing practices. We have then that I've identified that the majority of papers are basically just expanding on to other applications and not too much on developing new methods in order to create new learning frameworks for learning from demonstration. So the main idea here is that we have a solid foundation of learning from demonstration, and it promises a good integration into real environments. But we can see as well a missing practicability here, that the majority of experiments conducted in research are still very unrelated to the needs in the manufacturing or industry sector. So besides this obstacle, we also have that the task complexity and diversity is not yet on the level which industrial assembly would need. What I mentioned before, they are often looking only into 1 or maximum 2 subskills and not to the broader idea of assembly capabilities. Then the generalizability, what I mentioned at the beginning when I talked about learning from demonstration, is basically the capability of translating into new scenarios. The key aspect here is the change in the task. So if you use similar objects, that's really not really researched in this field, but it gives potential to look into it. And then 2 other steps. So if I have the time, or I'm actually have a lot of time still. Okay, so coming to my besides this literature review, to some other research contributions I've done in my PhD. I will talk about this very on a high level, but I'm happy to discuss like more details here or afterwards. So I was focusing on learning from demonstration for industrial assembly tasks, or to be more realistic, to be for assembly tasks in general. And I was looking into building or extending the research in learning from demonstration to some more advanced methods towards industrial assembly. So one of the aspects was actually so it's divided into the 3 phases I mentioned before for learning from demonstration. So in the first phase, in the demonstration, I was looking into a more efficient or more suitable and efficient demonstration method. So this work was in collaboration with Fred, so shout out to Fred. And we were basically looking into not using kinesthetic teaching, but instead removing the robot, what challenge might become available here. So the main challenge here is when you remove the robot and do some kind of passive observation, so the human is observed instead of just moving the robot, you actually miss out the capability or the kinematic capability of the robot itself. So when you demonstrate it, it becomes more the chance rises that even though you have done the task perfectly, the robot is not capable kinematically afterwards to perform the task. So in this work, we were basically looking in replacing the physical robot by a guided graphical user interface, which then indicates to the human operator during the demonstration what the robot is kinematically capable of doing in order to make the demonstration more successful and being capable of translating it into a successful reproduction afterwards. Then in the second phase, which is the learning phase, I was contributing to the field of looking into a very assembly-tailored framework in order to learn the task that is given from the human operator. So in this sense, I was basically looking into using so-called dynamic movement primitives, which is a proven and well-established learning framework for learning from demonstration, but I extended it to a industry-known framework from the predetermined motion time systems, which is methods time measurement, sorry. So it's an established framework in industry in order to plan and classify the most common assembly task in industry. So this one, so the methods time measurement framework, basically classifies or defines 5 different aspects in order to map most of the assembly tasks done in industry to this limited subskill repertoire. And this includes the reach, grasp, move, position, and release aspects. And then finally, in the reproduction, we were mainly focusing on how can we achieve a robust reproduction, even though if we have the relocation of the objects, an introduction of obstacles, and for example, as well, a user-defined workspace boundary. So this one was solved with some potential fields and recently being extended to control barrier functions with a huge input from Louis. So shout out to Louis if he's here. So with these 3 aspects, we're basically looking at the current or at the end of my PhD, the framework being installed in this kind of test bed. So I have a little video to share, which basically looks into the relocation of the objects. And then in the reproduction phase, we have introduced a new object, which the robot avoids while still doing the task. And here it's an interesting aspect. 1 second. When going back, I've intentionally gone outside of the workspace of the robot, but the robot, based on the potential fields applied, it remains within the workspace boundaries I've defined before. If you listen carefully, there's one aspect here missing, which is the first one of the guided demonstration. So I was using it in this framework, but I haven't recorded it here. So this video on the right side is basically from our contribution, or like our paper submitted to ICRA last year, or last year, I think. So it's basically looking into a welding task here, as you can see here. And then on the right side, we have this interactive graphical user interface, which we've developed in order to guide the human operator, or the participant in this case, through a successful task. Try it again. Unfortunately, the participant was standing right in front of the welding object, which is highlighted in green. The red voxels on the right side mean that the robot is not capable kinematically to achieve these points. So coming to the last point in this presentation. So basically, what I tried to tease out already, my future work or my plan for future work, which I've already started a little bit, is basically closing the gap between the research activities and the industrial practice by incorporating aspects of the four-step method, so making it more, being more smooth, integratable to industrial practice, and then challenging as well the test bed with real-world industrial tasks. So a concluding statement I would give you today is that learning from demonstration definitely offers a robust research foundation with the potential to greatly enhance the manufacturing sector. So it's now my task to transfer its capability to industrial practice. Not sure how in time, but thank you very much for your attention. And if you have any questions, please unmute or write a comment. Thanks.
Yeah, interesting presentation, Victor. I'd love to chat more with you. I think my comments go a little bit beyond what we can do in a few minutes.
Sure.
Rick Price. I'll mail you.
Oh, absolutely. Yeah, please.
I have a question, Victor.
Yeah, sure.
Thank you so much for that presentation. You made it really accessible for everyone, so I appreciate that.
Perfect.
I don't know, my question might be a little bit sort of from a novice point of view, but I wanted to ask, so we're talking about learning, and it seems to me that a very related concept to learning is knowledge. And I really appreciated that in your presentation you had that comparison between the learning from demonstration and then the training of the workforce. Yeah. So that kind of made me think about this paper I read recently, which came from psychology in the 90s, that talked about different types of knowledge that people have. And so if we sort of think about robots not just learning from demonstration, but learning to collaborate, I mean, we're talking about collaborative robots, right? Then what are the sort of, I guess, the types of knowledge that robots need to learn? Because people have different kinds of knowledge. We have situational knowledge and conceptual knowledge, procedural knowledge and strategic knowledge. And so, yeah, I was wondering if that's something like the types of knowledge that you're teaching.
Yeah, so I definitely have to look into the knowledge aspects. So, so I was mainly focusing on industrial assembly, which is from knowledge base quite low level. So I'm not exactly sure which type of knowledge it would be, but it basically is just mimicking the motion of the human. If you extend learning from demonstration has obviously be extended to a variety of different aspects where probably you see much more machine learning being implemented than the method I was using, which is basically just deterministic. So I think this knowledge aspect and then different types of knowledge comes more into practice or to be thought of in other aspects and not only industrial assembly, where you actually need kind of different types of knowledge. So I will definitely look into knowledge aspects and maybe talk to you later once I know what type of knowledge we have.
Great.
Any other questions? Maybe with my teasing question at the beginning, do you have sometimes as well this situation where you just look at a robot and see just a serial connection of motors and it's like, oh, that's not too cool. But then when it moves like in a unified behavior.
In the sound project that we did this past year in program 2, we found that adding the sound, it completely transforms the robot from being this sort of mechanical dead to like having sort of more like an entity presence kind of thing. So yeah, I think definitely experience, but then I find that different ways of sort of wrapping the robot changes that.
So I've got
Have you looked in? Sorry,
Victor, what about the upcoming humanoid robots? Because their kinematics is more similar to us. Same.
Yeah.
Will that make things easier?
That's what I wanted to mention a little bit. If we look into the traditional learning programming techniques, for example, here in lead through and walk through, or basically the kinesthetic teaching, you always need more degrees of freedom than you want to teach the robot, right? So if you have one single robot to teach, as the girl or woman here in this picture, that's fine. But if you have a humanoid, damn, how do you show like simultaneous movement of four, like 2 legs and 2? So I think that could be very challenging and kind of remove the possibility of using kinesthetic teaching.
Right.
But it definitely would apply as well to this. So I would say we look more into passive observation of like equipping the human with some kind of trackers or tracking the human body model in order to realize it. But yeah, that's a fascinating part as well, right? Like the humanoid robots and how they can learn similar to another human.
Yeah.
Comes scary already. It's going to.
There's just a message in the chat as well, Victor.
Oh, yeah, I'm not good in multitasking. Actually, that the kinetic and movement we are demonstrating is the best kinetic for the robot. Yes, so that's an interesting question, and it's correlated to a very present challenge in learning from demonstration, which is the correspondence issue. So it's not only the kinematic, so we move different to the robot, but it's also the perception. So we see things different to the robot, right? So for example, if we just think of how many sensors and how great our hand is, so we can be very sensitive and very, but then lift very heavy things at the same time with the same hand. That's definitely something to consider, and it could be integrated in a learning aspect. But yeah, that's definitely a challenge in learning from demonstration, which has been looked at, but probably not solved yet. So it's a common thing if you look into learning from demonstration, especially if you look into passive observation. So just doing however you would naturally do it on your own, it becomes challenging maybe to translate this knowledge to the robot, because he would probably, or it would probably have to move differently. But yeah, good question.
Yeah, so I guess I am going to speak. So the one thing is missing from the framework in which you examine these things, okay, is that in medicine, when they lay out the learning framework, they say see one, do one, teach one. And the teach one forces you to make the high level abstraction and planning. And so if you go back and look at where the bits and pieces break down, the ability to communicate, maybe like there's a whole field missing from the way you've looked at it, which is learning from instruction. So if you think about there's actually a dialogue happening between the instructor and the person. And when you do a demonstration, you're not just blindly doing a demonstration, you're also explaining what you're doing. You know, and so you're like, I'm going to pick this up now and I'm going to put it over there. I'm going to turn it over. So that it's that dialogue that's missing in the analysis framework that you're using for the overall set. Sorry, I mean, there's a massive conversation which we should have at some stage. But
but that's exactly what I wanted to point out with this comparison to industrial practice. So you have this very specific explanation during the demonstration and the execution of the learner, where they go, like during the demonstration, where the instructor goes through the performance of the physical demonstration, he clarifies as well the reasoning why it's doing it. And same in the execution, there's a justification of the key aspects. But that's kind of missing in most of the learning from demonstration aspects. So you have only one channel of communication here in learning from demonstration.
Yeah, so exactly. Okay, I missed it. That was the point you were making. So we're doing learning from demonstration in an industrial context with software and AI at the moment. And the hard part of the problem all comes back into the bidirectional communication in the steps. Because you want the robot to do what the robot can do, and then you want the robot to stop and ask when it doesn't know what to do. And so that bidirectional communication is super hard.
Absolutely. And I think that's still a research aspect as well. So historically, actually, there was like a separation of trends. So historically, learning from demonstration was either doing like low-level motion learning. So you look specifically on how the human has moved, but you have no knowledge of what the motion actually does or like what it means. And then on the other side, you have this, what you mentioned, the abstract level of understanding what it means, but typically they don't look at the trajectory to perform it. So picking up the apple and placing it somewhere else, that's kind of the abstract level. There's only a little bit of, so the trend is now combining these, or like the idea is that in order to succeed with complex tasks, you definitely need both of them. So you have to know what motion to do and on the abstract level, what this motion means.
Yeah, and it's that construing meaning from experience is a very interesting edge.
Absolutely, yeah. But yeah, good point.
So, Victor, I'll ask just on the same theme of this. Is there any work looking at how large language models or visual language models can be employed into this to facilitate some of that explanation and sort of multimodal input into the demonstration?
Yeah, so it's definitely something I want to look at. What I have seen in the research paper, so I was basically only looking into industrial assembly task or assembly-related tasks. There you had some papers looking into vocal commands, but very specific ones. So reaching and like not the large language models. But I assume there should be this trend coming up, especially it's an emerging field, right? So it definitely has some input to be placed here. If someone has done it yet, or like how advanced it is in the learning from demonstration area itself, I don't know yet, but I will definitely investigate it.
Yeah.
But yeah, it's a good point, especially in order to align as well these two frameworks, right? So
absolutely. Yeah.
Putting in some explanations, but doing these explanations intuitive and not like you have to say very specific words in order to succeed with a demonstration. But yeah, that's absolutely something to look at.
It seems like it's primed for that kind of.
Yes. Yeah.
It's a good one.
It has to come in.
Thanks. Very nice presentation.
Yeah. Thanks. Okay, any more questions? Just a last comment. If you have any comments afterwards, just send me an email. Or if you want to implement learning from demonstration in practice. Or if you have some interesting assembly challenges, then let me know. Okay. Well, Maren, I think I will just stop the recording and all the stuff.
Thanks very much, Victor. That was a great presentation.
Thanks.